In this video, we're going to study the third application of the principle of virtual work. As a reminder, there are three main applications of the principle of virtual work. The first one is finding the reactions of statically determinate beams, and we've presented a video about that. The second application is finding displacements at specific points for linear elastic small deformation beams, and this is studied in structural analysis courses. And the third application is finding approximate solutions. This application is the basics behind the finite element analysis method. We are going to present this application using an example. The example says use the principle of virtual work to find an approximate cubic polynomial displacement solution for the shown beam. And we need to compare with the exact solution for certain values of the P, the load P, and EI, and for the length as 1 unit, where E, L, and I are the Young's modulus, beam's length, and moment of inertia for the beam. And we are going to ignore Poisson's ratio. And so we have this beam with a concentrated load in the middle. There are two reactions, R1 and R2, and a third reaction, R3, that's equal to 0. And so the first step is to find the exact solution by solving the differential equation of equilibrium. The differential equation of equilibrium states EI, the fourth derivative of y with respect to dx1 power 4, is equal to q. The distributed load is equal to 0. And so integrating this equation, we get EIy is equal to this function, c1x cubed over 6, c2x1 squared over 2, c3x1, c4, where c1, c2, and c3 and c4 are constants to be obtained using the boundary conditions. We need 4 boundary conditions to find these constants. So we're going to use the symmetry of the beam to impose boundary conditions on this equation. The boundary conditions are as follows. On the left-hand side, the displacement is 0 and the moment is 0. So at x1 is equal to 0, y is 0, and at x1 is equal to 0, the moment, which is equal EI, the second derivative of y with respect to x1 squared, is equal to 0. The other boundary conditions are from symmetry. The rotation at this end, or in the middle of the beam, theta is equal to 0, and the shear force is half the load P. So at x1 is equal to L over 2, the shear, which is equal to EI, the third derivative of y with respect to x1 cubed, is equal to P over 2, and at x1 equal L over 2, the rotation, which is the dy by dx1, is equal to 0. So these are 4 boundary conditions. We can use them to find C1, C2, C3, and C4. And so by solving these 4 boundary conditions, by incorporating those 4 boundary conditions, we reach to the following equation. Y is equal to Px1 over 48EI negative 3L squared plus 4x1 squared. And this equation applies on the left part of the beam. If we repeat for the right part of the beam, we will get an equation that describes the displacement across the whole beam. And that equation will look as shown here. A certain equation when x1 is between 0 and L over 2, and another equation when x1 is between L over 2 and L. In order to find an approximate solution using the virtual work method, or using any other method to find approximate solutions, the first step is to assume a certain shape or form of that approximate solution. So for this application, or for this example, we are going to assume that the approximate solution is a cubic function. All the terms of the cubic function are a0, a1x, a2x squared, and a3x cubed. a0, a1, a2, and a3 are unknown constants, and we need to use the principle of virtual work to find these unknown constants. Before employing the principle of virtual work, we're going to simplify the approximate solution using the boundary conditions of the displacement. Because the displacement is equal to 0 when x is 0 and is equal to 0 when x is equal to L, we can get rid of 2 of these unknown constants. These 2 boundary conditions can lead to the a0 is 0 and a1 can be replaced as function of a2 and a3L squared. And so, after replacing a0 with 0 and a1 with negative a2L, negative a3L squared in the approximate y, we get the equation that y approximate is equal to this equation, function of x and L, and has two constants that we want to find. These are A2 and A3. Corresponding moment, m is equal to ei, the second derivative of y with respect to x1 squared, and so we need to differentiate y approximate, and so this is the moment as function of the unknown constants A2 and A3. In order to employ the principle of virtual work, we need to apply a virtual displacement. So we choose to apply a virtual displacement that is exactly similar to y approximate, but the difference is the constants that appear in y approximate, we're going to apply virtual constants A2 star and A3 star. Arbitrary constants in the virtual displacement field y star. The rest is straightforward. Internal virtual work, the equation states, is equal to the integral from 0 to L, ei, the second derivative of y with respect to dx1 squared, multiplied by d2ys star by dx1 squared. Using those two equations for y star and y approximate, we can integrate and we get these two terms. This is the first term and this is the second term. The external virtual work is equal to the external forces multiplied by the corresponding virtual displacements. The virtual displacements are equal to 0 at the supports, so the supports do not appear in this equation. The only force that we have left is P, and so P multiplied by the virtual displacement at x1 is equal to L over 2 is equal to negative P multiplied by the corresponding virtual displacement. When we state that the internal virtual work is equal to the external virtual work, for any choice of the arbitrary virtual displacement, that means that all the multipliers of A2 star on the left are equal to the multipliers of A2 star on the right, and all the multipliers of A3 star on the left are equal to the multipliers of A3 star on the right. So we get two equations in the two unknowns A2 and A3. So these are the two equations that are obtained by equating the multipliers of A2 star on the left with the multipliers of A2 star on the right, the multipliers of A3 star on the left with the multipliers of A3 star on the right. Here are the two equations again. These two equations have two unknowns. Our unknowns are A2 and A3. Solving those two equations, you find that A3 is equal to 0 and A2 is equal to PL over 16 EI, which means that the approximate solution that we're seeking that satisfies the equations of the virtual work is PL over 16 EI x1 multiplied by x1 minus L. To compare the approximate solution with the exact solution, we assume P over EI to be equal to 1 unit and the length to be equal to 1 unit, and we substitute in the approximate solution and the exact solution that was obtained at the beginning of the problem, and we plot both versus length, and you could see that the approximate solution is stiffer or gives a stiffer response than the exact solution. You get a lower displacement using the approximate solution than the exact solution. And when we start talking about the finite element analysis method, we will talk more about this application and how this application is used in general to find approximate solutions for displacements in a continuum.